All right, hey guys, and welcome back to some more AP Physics C. We're gonna start today with the I think this is the 23 the 23 set 2. So yeah, let's just go at it. And I got some, I guess you could call it new equipment. It's an iPad. I love the Apple Pencil. It's so useful. So we're gonna do that today. So we're just gonna start. So scientists have created a new type of lightweight foam and are performing experiments to investigate the properties of the foam. Mass of cart A is 1,000 kilograms. So the mass of cart B is 2,000 kilograms. A piece of foam with negligible mass is attached to the front of cart A. So there's the foam, and moves at a constant speed, with a constant speed, towards cart B, which is initially at rest. At time t equals 0, the foam connected to cart A makes contact with cart B. So it makes contact with cart B. The foam remains in contact with cart B for 0.5 seconds, after which the carts separate and both carts move with constant velocities. Okay, that's important. So here's this graph. The graph shows the velocity of cart A as a function of time for the time interval when the foam and cart B are in contact. So this is like time t equals 0 when the carts first make contact. So this is the time during the collision. So what features of the graph could be used to estimate the displacement of cart A during the collision? So we're just going to call back to our kinematics. So this is part AI. Basically, we need to understand that the integral under the v of t graph will yield displacement. So we're gonna use that idea and just put it into words. So the area under the graph as, and then we'll write the integral v of t, that's really bad, as integral v of t dt equals delta x. Done. That's the first question. So yeah, so the area under this graph will give us this displacement. That's just property of kinematics. Okay, using the information shown in the graph, determine the cart of speed, or the speed of cart B at t equals 0.5 seconds. So we need to understand that in this situation, dp dt equals 0. There's no external force acting on the system of the two carts. It's an internal impulse, internal collision. So we can use conservation of momentum, but we're going to be careful here. So we're going to say P final. I zoom in. I like zooming in. So we're going to say P final has to equal P initial of the system, right? But we're going to be very careful when we're saying this because you might think, oh, the carts attach, inelastic collision. No, don't even think that. Just think momentum is conserved. Don't think inelastic or elastic. Just say momentum is conserved, right? So we're going to think it's going to be P of cart A plus P of cart B has to equal PA final plus PB final, right? So PB was at rest initially, so that goes to 0. So the velocity of cart A would be the mass of cart A, which we said earlier would be 1,000 kilograms, right? Times, let's pull from the graph, the velocity of cart A was 5 initially, so, no, I scrolled past it, times 5 meters per second has to equal, times 5, has to equal, and the mass of cart B is 2,000. So it has to equal the velocity of cart A times its final velocity, which is 1 meter per second. So times 1 plus, and cart B was 2,000 kilograms, times VB. So you might be asking, where am I getting these numbers? Well, like M, it has to be, because momentum P equals MV. So we're going to do MA, VA initial, right? Has to equal, again, M, the mass of A, plus final velocity of A, right? Plus the mass of B, final velocity of B. That's the final momentum of B and the final momentum of A setting equal to the initial momentum of A using conservation of momentum. So now we have numbers here in one variable. All we have to do is solve. So this turns into 5,000 equals 1,000 minus 2,000 VB. VB. And we'll just do some simple algebra. This will turn into 2ms equals VB. And I should explain where I got that from. Pardon me, you guys. So we're going to subtract 1,000 to both sides, just some basic algebra. And we're going to get 4,000 equals 2000 VB divided by 2000. And that will cancel. 4,000 divided by 2,000 is 2, so VB equals 2 meters per second. There's my final answer. Done. That's the speed. So on the following grid, draw a smooth curve of the velocity of cart B as a function of time. Well, you might be thinking, well, we didn't get a function of time for cart B, so how am I going to know? All you need to do is understand that the momentum of cart B, right, it starts at 0. So here's our first y-intercept. Or, well, here's our y-intercept, right? And we know that V has to end with a velocity of 2 meters per second. So there it is. So if cart's A graph looks like that, has like, it turns from concave down to concave up, it's going to have a point of inflection. Well, B should do the same thing, right? And you might be asking, well, why is B going to do the same thing? Because whatever happens to cart A, there's equal and opposite impulse. It'll happen to cart B, right? So equal and opposite impulse. When this one's concave down, this one's concave up, right? When this one's concave down, this one will be concave up. That's one of Newton's, I think that's Newton's third law. Every object has an equal and opposite, or no, every action has an equal and opposite reaction, right? So this is an application of Newton's third law. So there we go, that's the smooth curve. So now here we go, so this is part B. The velocity v of cart A can be described by the function v of t equals 64t to the third minus 48t squared plus 5. Okay, calculate the magnitude of the maximum net force acting on cart A during this interval. Okay, so we need to understand that the maximum net force is on cart A is the mass of A. So the force acting on A as a function of time is the mass of A times the acceleration of A as a function of time. So how do we get acceleration of A? Well, acceleration of A is dv dt, which is going to equal the derivative of v of t. So the derivative of v of t, I'll just write it like this. So v of t was 64t to the third. Oh, what is that? Minus 48t squared plus 5. Great. So that the derivative is going to be, what's 64 times 3? Okay, 192 minus, and then 48 times 2. 48 times 2 is 96 minus, so 192t squared minus 96t, and then the constant is dropped because it's a derivative. So here's my a of t. So in order to get force as a function of time, I'll just multiply by the mass of cart A, and here's my force as a function of time, right? So here's f of t. And now on this exam, you will have Desmos. So let's just plot this. 1,192x squared minus 96x. So this may look like straight lines, but no, it's actually a parabola. It's just a really big, oh yeah, there's the vertex. It's just a really big parabola. So I'll go back to home. I think that's the function. Yeah, right? Yeah. So the maximum net force acting on cart A from 0 to 0.5 is it's all the way down here. It's a really negative number. I'll just scroll back down. It is a really negative number. Here we go. So max is at negative 12,000, right? FA max. And the magnitude of negative 12,000 newtons, sorry, that's newtons, equals 12,000 newtons. Now for this specific exam, what they wanted you to do is find it using algebra or calculus. So basically you just have to understand that this is a parabola and you would find the zero or find the maximum by finding the vertex, but we're not going to do that. We're going to use calculus. So the way you would find the maximum of a function is by taking its derivative. So we're going to pull this all the way over here. We're going to take the derivative of that again. So it's going to be 1,000 times what's 192 divided or multiplied by 2. That's 384t minus 96. and that's the derivative. So when you use the derivative to find the maximum, you're going to take the derivative of the function in which you want to find the maximum and set that equal to 0 to find a critical point. So this 1,000 just goes away, and now it becomes 384t equals 96. So let's divide 384 div 96. So at t equals 4, ooh, uh-oh, that's not good. Oh, it's not 384 divided by 96, it's 96 divided by 384. So at t equals 0.25 is when our maximum occurs, right? So now what you had to do, t max, what you had to do was plug that back into your original equation. This is the work they wanted to be shown. And that gives you, so I'll just plug that in, and it's 192 and 0.25 squared minus 96 times 0.25, negative 12,000. And now you do the magnitude, and then you get your final answer. So that's the work they really wanted. But you could also intuitively think that at the vertex it's its maximum used algebra, but this is a calculus-based course. It's way easier to use the calculus. So let's do the next problem. So on the following grid, draw a smooth curve of the magnitude of the force acting on cart A as a function of time. Clearly indicate the value of the maximum force on the vertical axis. Okay, so for this, you may be thinking, oh, well, the force is negative, so it's like that. No, there's nothing down here. They don't give us axes. So the magnitude means it's going to be positive. So basically what you have to understand is that the force is going to get really, 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 really big, right? It's going to reach its max, and it's going to curve down like a parabola. Literally, because it is a parabola. You have to recognize that this derivative is a parabola and plot an upside down parabola. That's what APC wanted from us here. I suck at drawing these, I'm not gonna lie. Okay, that's good enough for me. So what AP Physics C wanted for this specific problem is for you to just draw an upside down parabola and say at this line, here's 12,000 newtons. That's it. Kind of like that, right? So after you've done that, right, obviously it would be easier to just draw it along this line, but I hate drawing parabolas and I'm not going to draw it again. So yeah, AP Physics C, all they wanted was for you to draw an upside down parabola. Concave up would be incorrect because that would be to say that the force is decreasing. And the force was not decreasing over the interval because the initial force that was acting on it was 0, right? As per this graph, if I go back to home, 0, 0 is a point on the graph, right? And the forces, like here, the magnitude or the actual like value of the force, it was getting very negative, right? But it was still, the magnitude was still increasing. So because we're bypassing sign, that's why it's concave up, down instead of concave up. So the magnitude is the keyword. So let's continue question 1. The foam is removed from the front of cart A and the experiment is repeated. The carts collide with both cart A and cart B having the same initial and final velocities as in the original collision, Okay, the keyword. The time intervals during which the carts are in contact are different in the collision with the foam and the collision without the foam. In the collision without the foam, cart A is in contact with cart B for a shorter duration. Okay, so cart A is in contact with cart B for a shorter duration than in the original collision. Well, naturally, yeah, because when the two carts will hit, it's like almost instantaneous collision. But the foam makes them connect for a little bit longer. So here it's saying that with the foam, the carts collide for a longer time. Without, they don't. They collide for less time. So for the original collision when the foam was present, the magnitude of the average net force exerted on the cart is F1. For the collision without the foam, the magnitude of the average net force on the cart is F2. So on cart B, right? What is the relationship between the average net force F1 on cart B for the collision so F1 is with the foam and the magnitude of F2 without the foam. So before I even pick anything, I'm going to think this through. In order to change the momentum, we're going to think J equals delta P, which is equal to F net delta T, right? And that's pulled from your equation sheet. You can just think about that. So since the change in momentum in both scenarios, like it's set up here, the same initial and same final velocities, which is what momentum is dependent on since mass isn't changing. The same initial and same final velocities for both situations means that delta P will be the same in both situations. For a shorter time duration, the force has to be bigger because if this one goes down, this one has to go up to account for the change. So that means that the force on F1 on the collision with the foam has to be less than F2 without the foam. So I'll check that one. So what the? Okay. Since in the collision without the foam, delta P was, my handwriting sucks, sorry guys, the same with the collision with the foam, delta P must be the same. And since delta T was less for was F1, F2 for F2 slash scenario 2, F2 must be greater to produce I'll say, account for the change in delta T. Less delta T, higher higher F2. So basically all I'm saying is that since this one decreased, this one had to increase because this one was the same. Done. Okay. And that should be enough for them. Yeah, so let's see. So question 2, a student conducts an investigation to determine the relationship between the period of oscillation T for a system consisting of a block of N attached springs. Okay, the student, I should close these out. The student starts with a block of mass M attached to a single ideal spring constant of spring constant K, shown in figure 1. The student holds the block so that the spring is neither stretched nor compressed at a vertical height 1 meter. So it's at equilibrium above a motion detector. The student releases the block from rest and records the period of oscillation consisting of the single spring and the single block. An additional identical spring is attached in parallel. Okay, in parallel. Right? Shown in figure 2, the procedure is repeated for n equals 2 springs through n equal 10 springs. Cool. Derive an expression for t as a function of m. Okay. N. So, and then we have to use these constants. So simple harmonic motion, the period of a spring is 2 pi square root m over k. So we need to derive, so m as a function of n is going to be n times m. Because, sorry. Oh, wait, not m, nm. I'm an idiot. Excuse me. So the mass is actually not changing. The spring constant is what's changing. So the KEQ, the equivalent spring constant as a function of m, is k times n. Because springs connected in parallel, right, have their equivalent spring constants to add. But springs connected in series is the 1 over k, right? Like from E&M when you do like capacitors. So springs follow capacitors basically. So we'll add these spring constants in order to get the equivalent. So I'm just gonna plug in this for my equivalent spring constant here. Well, I should write KQ here. So then T as a function of N has to equal 2 pi, since that's not changing. M will be the same, and we're gonna write Kn. And there's our equation. Beautiful. Because mass isn't changing. All right. On the following graph, or on the following axes, sketch a graph of t as a function of n for n is greater than 1. So we know t from our earlier equation is proportional to the square root of 1 over root n, or sorry, 1 over the square root of 1 over n. So let's plot that in Desmos. So the square root of 1, just to get a feel for what the graph will look like. So it'll be concave down and decreasing. So that's pretty much all you have to do here. Oops. So for n is greater than 1, I'll just call this like n equals 1. And we can draw it from like here, concave up, concave down, and concave down, concave down. I can't draw concave down. Let me. Ah, that's good enough. Concave down, decreasing. Sorry, excuse me, not concave down, concave up, because it's like a smiley face. Concave up and decreasing. So there we go. So the only reason why it's concave up is because I looked at Desmos, I was like, okay, this is proportional to this, so I'm going to draw it as if it were that function. Sure, it'll be scaled, it might have a different intercept, but you don't have to care about that. They just want a ballpark for that specific question. So the student plots data for t squared as a function of n to the negative 1, which is just 1 over n. As shown, draw a line of best fit for the data. So this is why I love this iPad, because I can just do this. So let's align this according to the data. What do you guys think? Like there, right? Ish. That's good. I'd say that's a pretty good line. I like that line. Erase this. Okay. So cool, I did that. The mass of the block is measured to be 1.5 kilograms. Using the graph, calculate an experimental value for the spring constant K for a single spring. Okay, so let's pull back that equation. So it was T as a function of n is equal to 2 pi square root m over n k, or kn, right? So if I get T and I square it, that's going to equal 4 pi squared times m over nk. So I'll rearrange this a little bit so it'll become linearized. So 4 pi squared over k, we'll include m in this numerator, and then times 1 over n. Now if you see, it's starting to look something like y equals mx. So we'll make this statement that slope has to equal this 4 pi squared because we linearized the equation, 4 pi squared over mk. And then we'll rearrange it so we solve for k, so that k is equal to 4 pi squared m, 4 pi squared m over slope. So as I said, well, like you might be asking, where'd you get slope from? Where'd you get that equation? I just moved this one to that side and move that one to that. So it works because if I multiply by k on each side and then I divide by slope, it just allows me to swap them. That's just like a property of algebra. But now we have to figure out, okay, well, what is slope? Well, slope has to equal delta t squared over delta n to the negative 1, which is equal to, so this is where we pull points from our line of best fit. So let's pick one. Wow, we got lucky. 0, 0 is a point. So we'll just write that down. 0, 0. And let's pick another point. Let's pick an easy one. Here's like smack dab in the middle of whatever that is. And so it's what on the x? What's in between 0.8 and 0.9? 0.85, yeah. 0.85, comma, and what was that number? 10, comma 10. These are scaled correctly, right? Seconds? No, okay. So we're going to say 10 minus 0, change in t squared, 0.85 minus 0. And that's going to, now we're going to use Desmos, which is roughly equal to, oops, that is 0.85, right? Okay. Which is roughly equal to 11.7647. Now we're going to do the algebra. We're going to take that equation and we're going to say, we're actually going to pull this back over here, up here, and we're going to say 4 pi squared times, what was the mass that they gave us? 1.5 divided by 11.7647 is roughly equal to k, which is roughly equal to, I should draw a dotted line here, which is roughly equal to, I'll just write it down here. Let's put that in decimals. 4 pi squared, 1.5 divided by 11.7647, which is roughly equal to 5.0335 Newton meters. Beautiful. Done. So there's our answer. The student finds, so part 3, or part I. The student finds that the value given by the manufacturer for a spring constant is larger than the value determined experimentally in part CII. Determine a single source of experimental error that could result in the observed difference in the value of k. For the value of k. Briefly justify your answer. Okay, so it's the spring constant's larger, so let's see, what's proportional to slope? Let's say if we increased like the change in period, that would make slope bigger, which would make k smaller. So not a bigger period, so maybe a smaller period. So that the slope, yeah. So let's say the period measured. So just so you guys get a reference for the metrics, if the period measured was smaller for all of these same values, this line would look more like this, right? And have a less steep slope. So a lesser slope, lesser here, would increase there, right? And we get a bigger k. I'm just gonna erase that. Oh my gosh. I'll just go back. So the t squared second squared measured, well, I'll just say periods measured. Ooh, wait. Sorry. For reference, this one would have been smaller than the actual. So let's say this is what the actual periods have had to be. This slope would be smaller than the actual, which would decrease k, if that makes sense. So we'll go with that. The periods measured could have been, my handwriting sucks, sorry guys, too small. Oops. Decreasing slope overall. Wait. Ah. Sorry guys. Another error. Too big. Too big. And increasing. Increasing slope overall. Decreasing. Decay measured. Here we go. So the reason why I put the slope could have been too big, right, is because if we had this, a lesser slope, that would increase the k into what it actually would have been. But since our periods could have been too big, that would have decreased our actual k, if that makes sense. If anyone needs me to explain it further, just tell me in the comments. I'd be glad to explain it. But bigger slope, right? Lesser k. Bigger slope, lesser k. Right? Since I'm assuming we had a bigger slope because they're asking us to determine a single source of experimental error, right? Because bigger period, bigger slope. There we go. Okay. The student conducts a similar investigation to determine the relationship between the period of oscillation T, consisting of a block and a number n of identical springs, but arranges the block's spring system horizontally on a table. Frictional forces are negligible. In each trial, the block is displaced the same horizontal distance from equilibrium and released from rest. The student plots t squared as a function of n to the negative 1 for this new data. Would the slope of this best fit line be greater than, less than, or the same as? So the same as, because in our equation here, there's no gravity, right? There's no dependence on gravity or any other force. So n is independent of that. The spring constant is independent of that, and m is independent of that. So because t, because t of n equals m over nk, the period is independent. Period, I guess you could say squared, is independent. Independent of gravity / gravitational forces. And therefore, I guess you could, not period squared, sorry, the slope. So because that equals that, and slope equals 4 pi squared m over k, the slope is independent of gravitational forces and dependent only on variables that's independent of gravity, therefore same slope. So what I'm trying to say here is basically 4 pi squared is a constant, doesn't depend on gravity. The spring constant doesn't depend on gravity because it's a property of the spring. Mass is not dependent on gravity, so nothing really changes here. The period won't change. When n equals 1, the maximum speed of the block is found to be Vmax. So in this horizontal situation, when n increases, will Vmax increase, decrease, or stay the same? So let's think about it. We're going to use conservation of mechanical energy in simple harmonic motion because Vmax is a w squared, right? So this is an equation, sorry, not squared, that's a max. So in simple harmonic motion, this is the equation you can memorize. The maximum velocity of a simple harmonic oscillator will equal its amplitude times its angular frequency, right? So what's the angular frequency of a spring? W spring block. W of a spring block system is the square root of the spring constant. In this situation, the equivalent spring constant would be Kn over m, which is equal to square root KEQ. I'm just pointing out that this is how the equation works, right? And I can prove this to you on the equation sheet. Let's go back. Let's go up and look at that. So there's this equation for simple harmonic motion. It looks like this. So if I turn this into Vmax, this will be V equals Vmax sine Wt plus phi. So the point being is that at its max velocity, this sign will basically go to 1 and V will equal to Vmax. Actually, I can't prove that. Just know that it's a characteristic of simple harmonic motion, right? So when V equals Vmax, that will equal AW. Let's go back down. Right? Therefore, V max equals a the square root of kn over m. So if n is increasing, Vmax must increase because they're directly proportional. So we'll say increase. Therefore, since the square root of n is proportional to Vmax, Vmax increases. Will increase if n. There we go. And we can also think of that about it in just terms of the spring. So because if we compress at the same distance, if n increases, also because a / x naught initial displacement is the same. Just a little side note. So because that little initial displacement when they told us up here released from the same horizontal distance, the amplitude will be the same for each situation. The springs will be able to store this like bigger mechanical energy if they have the same displacement, because 1/2 kx squared, this will be the same. This can store more energy, right? That'll turn into kinetic energy. So higher initial stored spring potential energy, higher kinetic, and there you go. I just chose this equation because it seemed easier to me, but you can go the energy route or you can go this route. So let's go to the next question. A wind turbine includes a 3-blade system, oopsie, that rotates about an axis through each end of the blade. Okay, that rotates about an axis through each end of the blade, as shown in figure 1. Each blade has a length L and mass M, located at distance, with a center of mass located at a distance L over 3 from the axis of rotation. So we see that up here. Derive an expression for the rotational inertia of the 3-blade system. So we'll call that I. We'll call that I total. We'll call that actually I sys. Express your answer in terms of M, L, and physical constants as appropriate. The rotational inertia of each blade through the axis through its center, about an axis through its center, is given by this equation, 1/18 ml squared. So here we have to think, okay, this is where it's going to rotate, right? But this is the center of mass. Like if I imagine this out of the page, that's the rotational inertia equation we're given through the center of mass. This is when it's going through here and it's going to rotate like that, or like, well, it doesn't really matter if it's just going to rotate about that. So what we need to do is use the parallel axis theorem here. So we're going to do that right now. So we're going to say I prime is equal to ICM plus MD squared. So let's think, oops, sorry, I hit my mic. So the ICM is so this is for one singular blade, right? One singular blade, because its axis of rotation will be L thirds away. So the mass of the blade is still M, right? And the distance from the center of mass they told us was L thirds, and we're going to square that. So now we're going to bring this over here. We're going to have 1/18 ml squared plus ml squared over 3 squared is 9. So we can add this up. We can turn this into 1/18 ml squared, just manipulating some fractions, right? And now we can add these to become 3/18 ml squared. Simplify this fraction into 1/6 ml squared, and that's equal to I prime of one blade. So how do we get the total rotational inertia? So the total rotational inertia, or the rotational inertia of the system, is equal to the sum of the individual rotational inertias. So I ignore that. This is just how they like to denote it. So the sum means if I'm going to have 3 blades, I'm going to have to do 3 times 1/6 ml squared, right? Because that's going to be 1/6 ml squared plus 1/6 ml squared plus 1/6 ml squared, and that will give me 3/6 ml squared, which turns into 1/2 ml squared, aka our final rotational inertia. There we go. While the wind blows, the 3-blade system operates at a constant angular speed W naught 2.6 rad per second. The length of one blade is 36 meters. The numerical value of the rotational inertia of the system is I sys. Okay, they give us 6.7 times 10 to the 6 kilogram meter squared. Calculate the time t it takes the outer edge, so the outer edge of a singular blade to complete one revolution. So they give us this for a later problem. Don't even worry about that. What we need to recognize is that this is angular kinematics. So to complete for one blade, I'll draw it like this. To complete one full revolution, that's 2 pi rad. So if it's constant angular speed, we're going to recognize that W equals delta theta over delta T. And we're going to take delta theta and divide it by W to get delta T, also known as T, the time it takes to complete that whole outer thingy, or outer rotation. So we're going to state W equals delta theta, delta T, and we're going to turn that into T equals delta theta divided by W. Oh, so one full rotation is equal to 2 pi radians over, and it said 2.6, which is roughly equal to, so 2 pi divided by 2.6 is roughly equal to 2.41661 seconds. Beautiful. Next question. When the wind stops blowing, the angular speed of the system decreases. The angular speed of the system while slowing down is given by a function of time, as a function of time, by the equation W equals W naught e to the negative B naught t, where B naught is a constant with appropriate units as shown in figure 3. Okay. So it's going to say calculate the energy dissipated from t equals 0. Okay, so the energy dissipated when the wind stops blowing until the system comes to rest. So this is when the wind stops blowing, and this is, well, somewhere when the system comes to rest. So we're going to have to realize is that E dissipated is equal to the change in mechanical energy. So let's recognize when the little system, like the 3-blade system, I'll just draw it like this, is blowing, it has angular velocity, which means it has angular kinetic energy. So that's the only energy it has. We're not going to even consider the gravitational potential because its center of mass is staying at the same height the entire time. So we don't have to care about that. So its rotational kinetic energy, and it doesn't have translational either because its center of mass is not moving and rotating at the same time. So we don't have to care about that. We just have to think the change in energy must equal the change in rotational kinetic energy because it has rotational kinetic when it's initially when the wind stops blowing, but it doesn't at the end. Its rotational kinetic energy will go to 0. So we're going to say K rotational initial, or no, sorry, K rotational final minus K rotational initial. So we know that the final rotational kinetic energy is 0, which is easy because when the wind stops blowing, its angular velocity will equal 0, and rotational kinetic energy is 1/2 the moment of inertia, W squared, correct? So if this goes to 0, this must also go to 0. So now we're going to say, we're going to take this entire thing, since we just, E dissipated is equal to negative 1/2 I W naught squared, because W naught corresponds to initial rotational kinetic energy. So let's pull W naught from the graph. So here's 2. Okay, here's 2.5. Did they even give us? Oh, 2.6 rad per second. Great. So it's 2.6 radians per second. I was trying to pull it from the graph, but no, they told us its initial angular speed, well, the constant angular speed when it was rotating was 2.6, so that will be our initial. So let's do negative 1/2, and the rotational inertia was 6.7 times 10 to the 6th. 6.7 times 10 to the 6th, 2.6 squared, which is roughly equal to, let's put it in our calculator. And I love Desmos. I suggest all of you use it on the AP exam instead of relying on your own calculator unless you're asked to take a numerical derivative, because Desmos can't do that. Okay. Which is equal to negative 226460000 joules. Bam. That's the energy dissipated. We can move on. So 2 million joules, that's a lot of joules. Let's move on. Derive an expression for the net torque exerted on the system as a function of time as the system slows down. Express your answers in terms of B naught, W naught, M, L, and I system. And physical constants is appropriate. So the net torque we need to recognize from Newton's second law in rotational form is equal to I alpha. And you may be asking, well, why don't you use R cross F? I totally could do that. I'm not going to because I don't know this, right? But I do know the rotational inertia, and I do know the W as a function of time. So I'm going to use the fact that I know W as a function of time in order to get to alpha as a function of time, because what I'm going to write next here will explain it, because the derivative of W with respect to time is equal to alpha. So I'm going to, oh my gosh, d dt. So kind of like the beginning of this exam, we're going to take the derivative of a velocity function to get to an acceleration function. So alpha, angular acceleration, it was W naught e to the negative B naught. b naught t. Okay, there we go. So a constant multiple will stay a constant multiple, and we'll get w naught. And now we have to use the chain rule. E to any power, right? We're going to say e to the u's derivative will stay e to the u. And then du dt will give us negative b naught, right? So the chain rule, we're going to differentiate e first, which will give us e negative b naught t times the derivative of this, which will be negative b naught, just negative b naught. So this turns into negative b naught w naught e to the negative b naught t. Great. But that's just alpha as a function of time. In order to get the net torque as a function of time, we're going to have to multiply that by I cis times alpha as a function of time. So if we're just going to multiply b naught I cis w naught e to the negative b naught t. This is a lot. That's our torque. Equals torque as a function of time. Done. That's the answer. And that's in all of the constants that we get. So we can leave that there. So that's the net torque, right? If you have any questions, go ahead and ask them. I went through that a little quickly, but mainly if you have questions about the chain rule right here, I would suggest looking up the organic chemistry tutor. He goes through it really beautifully. The reason I didn't just leave it as b naught and multiply by negative b naught is because I had to apply the chain rule. Because if this was just t by itself, I could say this derivative would be w naught e to the, I guess you could say t. But because it wasn't, I have to multiply by its derivative using the chain rule because there's a function inside of a function. That's part of the calculus of this course. So let's get into it. The next one. Derive an expression for the angular displacement delta theta as a function of time t. Express your answer in terms of b naught, w naught, b naught, w naught, ml, and so basically the same constants as before. So what we're going to do here is we're going to be very careful. We cannot do this indefinite integral of w of t dt. Well, we could, but we're not going to because we would need a plus c, right? Which would be our initial w naught that we have to pay respect to. So we're going to go ahead and just integrate it from 0 to t like we would any of our, when we're doing like resistive forces. In this situation, we're going to integrate from 0 to t. Usually in physics, you'll want to integrate from 0 to t, but in calculus, on the AP Calculus exam, they don't like you doing that, so don't do that. So we're going to integrate this function, dt equals delta theta as a function of time, right? Which is going to give us the integral from 0 to t of, and you may be asking, well, why is this effect? It's because d theta dt gives us w of t, fundamental theorem of calculus. The integral will undo the derivative and get us back to theta as a function of time. So let's actually handle the integral. So it was w naught e to the negative b naught t dt. So I think that's the right function, correct? Yeah. So we're going to pull out our constant w naught, integrate again, 0 to t e to the negative b naught t dt. We're going to use our calculus rules that AP Physics C gives us. If we go, I'm not scrolling that far. If we go up here, oh, you'll have to forgive me. I have to close this. If we go up here, oops, okay, you'll recognize that when I'm going to integrate e, I need to do 1 over a, e to the ax. So because it was e to the negative b naught t, that will integrate to 1 over negative b naught, e to the negative b naught t. So that's just our calculus rules, right? We'll just leave that there. And we'll go back to that page where we were, which is right here. So let's go ahead and do that. So that will integrate, like I said, to w. Because the w naught was outside, I have to pay respect to it. It'll be w naught. When I say pay respect to it, I really just mean make sure it's there. So e to the negative b naught t will stay on top, but I have to add that negative b naught from 0 to t. And now since I have a negative, I can just switch my bounds and get rid of it because I don't like working with the negative. So we'll say W naught e to the negative b naught t over b naught. And we'll switch our bounds from 0 to t there. And now I'll pull out my constant and actually take the integral and of e to the negative b naught t from 0 to t. And that will give me w naught b naught. When I plug in 0 there, I'll just get 1 because e to the negative b naught times 0 is equal to e to the 0, which is equal to 1. 0 to anything is 1 except for 0 to the 0. Don't ask me about that. That's not related to this course. So it'll be 1 minus e to the negative b naught t because we're subbing in b naught t for t. It's weird. You could use a dummy variable, but I'm not going to do that. And this is my final delta theta equation. So I'll just say equals delta theta as a function of time. Circle that so the readers know. And bam, there's my function. Done. So if you were to have done it as a definite integral and thought about the plus c, you would have had to think, well, what's the initial angular displacement? Call that, let's say, 0, and then you would have to go through. No, don't do that. In AP Physics C, when you're given a function and you have to integrate, like when you're given angular velocity function of time, they want you to get the displacement as a function of time, like the angular displacement, or velocity as a function of time, they want you to get to displacement as a function of time. Usually just do 0 to t unless they give you the initial displacement or like the initial position, right? So that's basically just what we want to do in AP Physics C. But if you have any questions related to like that or anything else, leave them in the comments. I'd be happy to answer them because this is what they wanted from 0 to t in this situation. So they actually have a point for bounds. So let's go to the next one. The 3-blade system is now replaced with a second 3-blade system identical to the first, except the second 3-blade system slows down to this equation. W equals W naught e to the negative bt, where W naught equals the same as before, 2.6 radians per second, but B is greater than B naught. So it says they want us to sketch the angular speed for the second 3-blade system as a function of time t. So what I'm going to do is I'm going to visualize this. So I'm going to call W naught 2.6 in decimals. We're going to visualize it in decimals. E raised to the negative, let's call B naught 2. X. So that's how that one. Now, if we increase B naught, like the problem did, because B is greater than B naught, what would happen? Let's say we call it 4x. So that one has to be under it the entire time. So that actually be steeper, like this. So that's what they wanted. They didn't want that. They didn't want that. No, they wanted to see that it's under it the entire time. And I can just do that by looking at the trend on Desmos. And that's the end of the exam. So I hope you guys enjoyed that. This was honestly one of the more enjoyable exams that I've gotten to do. And I wish you all luck on your AP exams, considering today's April 12th. April 12th. The Physics C exam, the mechanics. I think mechanics comes first. So there's 28 days, 18 days left in April, plus 14. What's 18 plus 14? 18 plus 14. Well, really 13, because the day of. We have exactly a month left until the AP Physics C mechanics. So, and then a month and a day until E&M. So I'll hope I can push out E&M videos soon, but I wish you all luck on mechanics. And yeah, stay tuned for more videos.